Hennie, which are giving a talk on foundations first, enhancing TSF investigation with geophysics, practical case studies demonstrating foundation characterization. Thanks, Hennie.
Okay, hi everyone. Yeah, I think let's get straight into it. I'm just going to run through a quick introduction. As I'm coming from the tailings background, just a quick glance at the GISTM, so that will pop up in all of our presentations. Then instead of sites, I chose an example site, only one site, a copper mine in the DRC, and I think it's going to fit quite nicely in with the following speakers focusing on the dolomite aspect as well. Going through the regional geology and different aspects, conclusion, and then just the introduction to the team. Okay, so this presentation aims to highlight how an iterative process is sometimes required to actually satisfy or align with the GISTM requirements, while showcasing the added value of integrating geophysics into the geotechnical investigations, specifically for tailings facilities. And this is obviously based on an example project. The GISTM provides a global framework for the safe design, construction, operation, and closure of TSFs, emphasizing the need for a thorough understanding of subsurface conditions. That includes both the foundation as well as the existing tailings. So achieving this often requires multiple rounds of investigations. It's not a once-off thing, where both geotechnical and geophysical studies are planned, conducted, and refined to reduce any uncertainty. Again, just a quick glance, the 6 topics that Adrian and James already alluded to, I'm going to skip over that and just focus on this topic 2 and topic 3. I think that's where the geotechnical investigation and geophysics actually plays an important role. So topic 2, that integrated knowledge base, it requires that operators develop a robust knowledge base, including geological, geotechnical, hydrogeological, geochemical, climatic, and seismic data. Geotechnical and geophysical investigations form part of this knowledge base. And topic 3, which is the design, construction, operation, and monitoring side of things, it requires that facilities be designed and operated using a defensible geotechnical model, for example. So again, both the geotechnical and the geophysical aspects quite important here. So the data derived from the investigations are applied here, for example, any stability analysis, seepage control, construction, QA, QC, and ongoing monitoring as well. You'll see here that I make no reference to the actual location or name of the client. This is still an ongoing investigation, which was a little bit more complex geological setting, and I thought it might make for a good topic for today. The regional geology, again, I'm not going to delve into this too much, but the site is in the DRC. It is a copper mine, so it forms part of that Lufilian arc. This Lufilian arc, the whole copper deposit, it's actually from Zambia extending to the south of the DRC and towards the northeastern portions of Angola. More site-specific information, the site is positioned on the Kundalungu group, which is typically comprised of diamectites, acting as a pebble marker within the stratigraphic sequence. The typical rocks that we anticipated for this site included sandstone, siltstone, shales, and then I highlighted here a dolomite and limestone. The geotechnical investigation, again, the iterative process of geotechnical investigations. We were approached by the client to conduct a predetermined geotechnical investigation for an initial TSF outline. The pit is located to the west with an existing TSF to the north of the site. Since these positions or the investigation positions were predetermined, we basically followed this sort of grid layout across the basin, as well as covering the wall with a number of test pits. I think it was 25 test pits for the wall and 15 test pits within the basin of the TSF. And usually as like these things play out, after we conducted this investigation, there were some additional requirements from our side, which included 5 rotary core borers to at least address the wall to an adequate degree. After we conducted that, there was a change in the layout and the position of the TSF. So again, The first question would be, what is the gaps in the geotechnical investigation collected? And we had to go back to site and conduct an additional geotechnical investigation for this new layout. This actually included, again, covering the wall portion that was not previously investigated, and that included 13 test pits all along the outer boundary of this wall. It also included drilling an additional 4 rotary core boreholes, just to ensure that there's no change in the site conditions as we previously encountered. The rotary core boreholes were all extended to 25 meters, and it basically comprised of colluvium at surface, residual siltstone, and then siltstone at the base with some shale here and there. So quite a simple profile in terms of the shallow underlying ground conditions. We requested some historical information from the client, and this is where the valuable information actually start to pop up. The information that they had close to the site included historical condemnation boreholes. They provided us with these logs, and after quite a bit of a review of these logs, coming up with some simplified sort of lithological units, we actually identified that they logged in several holes. They logged dolomite that's directly underlying the site, and in the holes they specifically alluded to cavities that was present during the percussion drilling exercise. So again, coming from the GISTM background, the next question that the ITRB would most likely ask is, well, what have you done to actually satisfy the question of whether the site is now underlain by dolomite, and specifically pertaining to, even though it's small cavities, what information do you have to support this? We also had a look at INSAR data, and we identified potential subsidence zones within the footprint of this TSF. So again, rotary core borehole and test pitting provides very specific information for specific positions. So the next step was to actually motivate for geophysics. I just quickly want to, maybe for the audience here, not everyone is from a mining background, just allude to the fact that condemnation boreholes is also sometimes referred to as sterilization boreholes. They basically drilled specifically to prove that a specific area does not contain economically viable mineral resources, and then they can actually allocate a specific area for potential other uses. And this is often then allocated for things like TSFs, waste rock dumps, and plant infrastructure in the future. You can clearly see there the dolomite and the cavities, and specifically that KLS, the fourth borehole there, you can see that cavities is actually within that upper 20 to 30 odd meters below the TSF. Quite an important thing. Again, drilling is like looking into earth through a straw, very limited information, and the best way to actually connect the dots is by means of geophysics. So we recommended to the client, let's go for a geophysical investigation. Typically, this included electrical resistivity imaging and MASW. This was proposed along the wall of the new layout for the TSF. Logistical issues delayed the geophysical investigation team with approximately 6 months. So if there's a question after this talk on what can be done from the geophysics side, is create equipment that can fit in a backpack and be flown up into Africa without any logistical issues. So I don't expect any other questions. As the geophysics was ongoing, eventually when they actually arrived on site, we also motivated for the dolomite stability assessment to be included. And this was actually in motion, given the dolomite and the cavities logged from the condemnation boreholes. The results from the MASW, here we immediately observed that if you look at line 1, L1 and L2, that they are significantly different when compared to L3 and L4. The white rectangle shows areas of low velocity zones present in higher velocity layers, possibly indicating fracture zones or weak zones. L1 and L2 typically indicated less stiff soil conditions, where L3 and L4 actually indicates quite a variable profile, with soil and rock conditions, with some areas being denser and some areas being stiffer. The electrical resistivity imaging, this kind of formed part of, or the scope for the electrical resistivity imaging was extended to actually inform the dolomite stability assessment. So generally when you do these dolomite stability assessments, one would opt for something like gravity. So why not gravity that's typically used for these investigations? Well, while gravity surveys are commonly applied in the dolomite stability assessment, in this case, the consideration also included cost, as well as the desire to avoid the logistical complexities that we experienced earlier in the project. But that's not all that we looked at. We also looked at the technical advantages offered by ERI when compared to the gravity investigations. So just to compare these two investigation methods, so sensitivity to karst features, and I think the geophysicists will know all of this, but just to quickly run through this, highly sensitive to cavities, clay infills, groundwater, and weathered zones, electrical resistivity. On the gravity side, detects only density contrast. Small voids are often too subtle to resolve. So those small cavities, as maybe a 1 meter or a 2 meters, might easily be overlooked with something like gravity. Resolution of features, electrical resistivity can resolve small-scale features, and you can actually design your investigation to have specifically targeted areas to provide additional resolution. Gravity, limited resolution, and requires a very dense station spacing to detect these small or local anomalies. Depth information on the ERI side provides depth-specific imaging, 2D or 3D resistivity section showing geometry of the anomalies. Gravity is depth ambiguous. Anomalies may represent shallow, small voids or larger, deeper features. The interpretation certainty, resistivity contrast link directly to material type, so your air, water or clay-filled voids. It's less ambiguous when tied to borals. The gravity is less specific, so anomalies can result from cavities, thicker swirls, lithological variation, or topography. Cost effectiveness, I think that the electrical resistivity is efficient for local surveys with grids or lines and provides rich data sets. Gravity can become quite costly at high resolution if a dense grid is needed for those small features and often more efficient on a regional scale. And then again, the ERI equipment was already on site, so it just made sense. Okay, then moving on to sort of the dolomite stability investigation. Although I'm not going to go too much into the stability investigation, the ERI data that we collected actually supported us in allocating or positioning the percussion boreal drilling that was done for the site. So this was both vertical and inclined reverse circulation percussion borals, specifically targeting areas identified by the ERI. As you can see here, we encountered overburden, the siltstone shell, again, also dolomite and cavities. This is now from the SRK percussion borals. And if we kind of summarize between the dolomite and the cavities that we encountered in the SRK as well as the condemnation borals, you can also clearly see that the southern and the western side of the TSF is actually underlain at depth by dolomite. We took this ERI data and with the support from Wesley and team, they created this 3D model for us, and we benefited greatly from actually taking this data and go through a stepwise filtering, which revealed a clearer lithological contact as well as potential fault zones. From the condemnation borals, there was quite a lot of lithological units, so it was difficult to actually assign specific contact zones to specific borals. So this information from the ERI actually indicated that we might be dealing with lithological contacts that's vertical to subvertical, as well as some areas that might be associated with potential fault zones. So again, the ERI contributed greatly to the understanding of the site and us refining our potential geological model in line with the data that we collected from the drilling exercise. Okay, so we went through a lot of background checks and went the whole academical route and coming up with a few papers and the data acquisition, evaluation, and the interpretation to actually inform this postulated conceptual ground model that we have for the site. And again, this is just showing from the information that the mine provided us, all of the documents that we needed to source, because it turned out to be a more complex site than we originally thought. Just to allude to that, the top figure there is a section of all of the boreholes, or a summary of the boreholes drilled by SRK. That's the percussion boreholes. The rotary core boreholes extending only to the 25 or 35 meters. You can see clearly not as complex as the deeper underlying geology. And then from the condemnation boreholes, if you can connect any of these lithologies, then that's a thumbs up without using the ERI as well. Okay, so again, taking all of this into consideration, we took a step back and said we're first going to come up with a simplified conceptual model for the site. This is still being refined. So this is kind of what we created for the site. We know that the western corner and the southern corner is actually karst ground, which formed part of the RIT and mine series. The north and the south, siltstone and shale, and we identified 2 potential fault zones. Although there's quite a thick cover in terms of the siltstone and the shale on site, that upper 15, 20, maybe 30 meters in some areas, we can clearly indicate that the site does have karst conditions, which needs to be considered as part of the design aspect of the TSF. And if there's any remediation that needs to be done as part of the construction of the TSF, then these zones can be used as a first pass that needs to be taken into consideration. So just as a conclusion, geophysics is not a replacement for geotechnical investigations, but it certainly forms a critical complement that broadens our understanding of ground conditions. An iterative process or approach combining drilling, lab testing, and geophysical methods is essential to reduce uncertainty and align with GISTM requirements. Geophysics enhances the efficiency by guiding, for example, the borehole placement, improving ground models, and identifying potential hazards early in the project phase. The decision to use ERI as part of the dolomite stability assessment as opposed to the gravity was beneficial for the site as it's considered a structurally complex site, and we have vertical to subvertical features encountered on site. The integration of geophysics with the geotechnical investigations makes for an improved knowledge base, again talking to the topic 2 of the GISTM, and it supports a defensible design and monitoring, again topic 3 of the GISTM. Ultimately, combining methods strengthens the risk management, improves decision making, and contributes to a safe, sustainable operation of a tailings storage facility. I just quickly want to allude here, this is a project team. Again, the project is still ongoing. All of us basically from SRK with Ilse as a consultant. So thanks for the work for so far. Thank you.
Awesome. Thanks, Hennie. Any quick questions for Hennie?
Thanks, Hennie. That was really interesting, especially given that we were talking about gravity quite a lot later on. But just 2 questions. One is very simple. Why the inclined RC boreholes? The second one is perhaps not just addressed at you, but more broadly at this forum, is the kind of sophisticated modeling that you did is way beyond the average one-man show who mostly does, who are mostly doing the stability survey, say in the Centurion area. Is it possible for the ordinary kind of small consultant to get access to this kind of modeling technology, either through geophysical companies or through yours or through the universities?
Okay, so I think to answer your first question, we were basically informed by the mine geologist that there might be a structure, but they didn't know exactly where it was. They did have some maps indicating a possible area where they think there's a fault running through. We decided that if we want to see that contrast, then the only way that you will actually, or the chances, improving the chances of us actually drilling through that fault zone will be increased if we do the inclined boreholes, and it added that value. Whether we actually encountered it to the degree that we thought we would, that's questionable, but we did try it with actually doing the inclined boreholes. And then if I can contribute on your second question, but it's again open for the floor. I do think there's value in, for example, coming up with these 3D models. I make use of Sequent products, Leapfrog, but those licenses are becoming expensive as well. So the larger projects actually benefit from this because it makes up for a small amount in the bigger scheme of the total project cost. But again, I was chatting earlier to Ilse, and for these dolomite type investigations, the first step will always remain a 2D approach before you go into more sophisticated type of modeling software. But open for the floor on that question.
Yeah, I think just to add from the geophysics side, the goal of this symposium, having everyone here, and the goal of a lot of the geophysicists is to make geophysics more accessible to engineers and not keeping it just in big exploration budgets. So the big goal for these 2 days, like Hennie was saying, is to look at how we can start meeting each other and start producing the required models that are useful for you in the long run. So yeah, that's the goal for these 2 days.
And designing equipment that fits in backpacks.
A comment on 3D modeling and geophysics. The PR papers in this area are very good, but hard, realistic evaluation shows that unless you have some deep borehole control on the features, the geophysically active features, which are intersected by boreholes, then the end result in a 3D inversion is essentially a blob. And some of the practitioners tend to prefer to do 2D inversions on parallel lines and then stitch those 2D inversions together to give a pseudo 3D. Over and out.
Yeah, I think there's different approaches to this. Again, you can only sort of realize or model in a 3D environment, but you will always have to go and do physical confirmation on whatever you present on this. But it does form part of a conceptual idea, and it makes the communication between the scientist, the engineering geologist, as well, the communication between the engineering geologists and the design engineers a little bit more simplistic in terms of their understanding on what they need to design for in early stages of the TSF. So certainly value in going the 3D route to the end of the day.
Heidi, I just have 2 questions. The first is about so in South Africa we have the SANS 1936 standards for dolomite investigations. Are there something similar for the DRC, seeing that they have dolomite in their country? And then the second question is the difference between if you had the choice, would you still have gone with the ERI to try and map the cavities or get information on the cavities, and also what is the spacing of the stations? Do you think it had, by densifying it, did it have give you a good enough resolution of those cavities?
Okay, so your first question in terms of standards, look, I think in all of these countries where they don't necessarily have these standards, you kind of refer back to something that we locally use. Again, for tailings facilities specifically, yes, there's these standards and guidelines, but I do think that there's maybe the potential, not necessarily to create a standard specifically for tailings facilities in the dolomite space, but to come up with sort of a good practice guideline to support the investigation requirements for tailings facilities that's being constructed on dolomite ground. So I don't think necessarily like a standard, but I do think that there's some good practice guidelines that I think can benefit the industry in the tailing space. Then in terms of your ERI question, I can not remember the spacing that we went with for this ERI investigation. I do think that there was a lot of benefits for us opting for the ERI in this instance. And I think the fact that we were dealing with quite small cavities closer to the surface from, as indicated in the condemnation models, I do think that ERI was the way to go as opposed to gravity for that specific site. Yes.
Awesome. Thanks, Hennie. I think let's close the session there.